Hello everyone and welcome to the second video for lesson 40-1, which is applying the addition rule or just the addition rule. This is on page 581. We're going to go through and do the first 7 problems. It eventually switches to page 582 for 5 and on. So let's just take a look at what we have here. If you're unsure what the addition rule is, there was a video before this that kind of went over generically what it is, but hopefully now putting some context to it will also help us out here to understand what's going on. So here they set up a problem. I retyped this so it might look a little different in your book. I think it's one paragraph. I kind of split up the lines. There's 100 houses on Hector Street. Some of those houses have attics and some do not. Some of the houses have basements and some do not. Let the set of houses that have attics be A. So we know here that A represents attics. And set of houses that have basements is B. And B will be basements. The number of houses with various combinations of attic and basement are shown. So how many of the houses on the street have attics? So remember, when you're looking at probabilities, you're looking at the entire circle. Right? So we want to include anything that happens in that circle. So here we have the amount of houses that have attics would be 29 plus 23, which is 52. So how many of these have attics? Anything in the blue? We got 29 plus 23, which equals 52 houses with attics. Okay, so that's what we have to start off with. How many of those houses have basements, or how many houses on the street have basements? So the same thing we just did, except we're going to do it for B. So we got this guy here, we're a circle, and it's a little sloppy. That's okay. All right, so we have B, which, again, I like to highlight things to help you guys out. Hopefully seeing the colors helps. B is the entire circle, so you got to make sure you add both pieces together, that little intersection piece in the middle and the just red piece on the right. So we have 23 plus 34, so 23 plus 34, which equals 57 houses with basements. Now, if you're a little little confused about what's going on here, you just have to understand that 23 represents people with both attics and basements. So when we say 52 with attics, we're not talking about basements at all. Yes, some of those people also have a basement, but that's not what we're talking about. So you got to focus just on attics. And same thing with number 2. 57 houses have basements. Yeah, 23 of those also have attics, but that's not what we're talking about, right? These are two separate numbers, two separate events. We're not really talking about the intersection of those two yet, which we will get to. So if a house is selected at random from the street, what is the probability that it has an attic? So we already know that there are 52 houses with an attic. So what we need to do is divide that by the total number of houses. If you didn't know what that was, you could add all the numbers together, the 29, the 23, 34, and 14. But it did tell you, if you were paying attention in the beginning, that it's 100 houses. Now, this makes our life easy because probability is basically, the number of the event, in this case 52 with an attic, divided by the total, which is 100. Dividing by 100 is a little easier here because it basically just moves the decimal places 2 points. So the probability that they have an attic would be 0.52. Okay, same thing with the basement, right? So we want to find the probability of the basement. We know that there are 57 houses with a basement because we found that for number 2. And again, we want to divide it by the total number of houses in this problem, which was 100. So the probability of a basement is 0.57. And you technically don't need the 0 there. I don't care which way you do that. All right, so that's just a quick rundown of kind of what's happening, how many basements, how many attics, what's the probability of those. So it's kind of a review of what we've done. So let's see how this goes further. If a house is selected at random from the street, what is the probability that it has an attic and a basement, right? So now we want to find the probability of A intersect B, because we want both of those things to happen, right? So that would be, and remember is the intersect, that's like an upside down U. So that would be just the middle purple part here. So we want to know how many houses have both these things. Where's the overlap of attic and basement? And that's 23. So the probability of this would be 23 divided by the total, which again is 100, which makes our life easy. You don't really need a calculator. Hopefully you just move that decimal place over to the left 2. So we get 0 or just 0.23, right? It doesn't really matter if you have the 0 or not. Okay, good. So that's kind of the setup, right? We have these three probabilities, A, B, and the intersect of A and B, which is 0.23. So we want to write the answers 3 through 5 using notation. Use set notation as necessary, whatever it says. I'm basically just going to go back up here. We're just rewriting the information we just found. I can copy and paste. You may have to physically rewrite it. That's okay. You can follow along and do that while I'm doing this. You can pause it at any time to write it in, whatever you need to do. They're not all going to fit in that one spot, so I'll spread them out. All right. So what is the probability that has an attic or basement? Right? So we want to know what the probability for the union of those is. So in order to do that, we're going to have to add the just attics, which is 29, plus just basements, which is 34, and attics and basements, which is 23. So if I wanted to find the probability of A union B, it's going to be still divided by 100, right? Because that didn't change. There's still 100 in total. But now in the numerator, I need to add the 29 plus the 23 for the combo of both attics and basements, plus the 34 of just basements, for 7 and 86. So that is 86 over 100, which is, and I'm going to skip the step of dividing 86 and 100 and go right to the answer, 0.86. Right, so that would have added up to 86 divided by 100, which is 0.86. So what is the value of PA plus PB? So the probability of A and B, we know the probabilities individually. So if I wanted to find the probability of A plus B, and probability of A plus the probability of B, you literally just add the two probabilities. So I know what they are from up here. So I can add that 0.52 plus 0.57. Now, and we end up with 1.09. At this point, that should be a major red flag because probability shouldn't be more than 1. That means 109%, which just doesn't exist in things, at least in probabilities. So let's take a look now. What is the probability of A intersect B, which we found up here, to be 0.23? So let's go ahead and take that. And we'll just rewrite that down here, even though I guess we had it up there too. All right. So explain why probability of A and probability B is not equal to the probability of A union B. So we can see that very clearly right here. The union probability we found to be 0.86, and we can see that that's not the same as 1.09. Okay. I mean, they're just not the same number, right? So beyond that, that's at least the first indicator that, okay, they're not the same, but why, right? So why aren't those two the same? Well, we got to think about where this 1.09 came from, right? It came from taking the probability of A and the probability of B. So we took those two things together. Well, where did they come from? Remember, A included both attics and basements, as did B. right? So when we find the probability of the union, we need all those three things. We need the attic, attic and basement, and just basement. So we need all three. But the problem is when we add the two together here, right, A and B, since A and B both had the situation of basement and attic, we're kind of adding it twice, right? That's the problem. We can't add that number 23 for both twice, which is happening when we add those two together. So why aren't they equal? Well, we're adding the intersection twice. So what we can do is subtract out the intersection. So let's see if that even works, right? We know that in this 1.09, the intersection got added twice. Well, what was the intersection? Oh, over here we found it to be 0.23. Well, what would happen if I subtracted out the double, that duplicate or the double intersection that's happening? Take one of them out, and we would get to the correct number, which is 0.86. All right, so that's kind of what's happening. So when we have this formula, we could use the probability of A and the probability of B to find the union, as long as we understood that if we're adding A and B together, we're kind of doubling up on the intersection. So I'm going to have to subtract it one time so that it's no longer doubled up. Right? And you're probably thinking to yourself, well, this is silly. Why would I do this? Well, you might have only 3 out of the 4 pieces of information. Maybe the probability of A and the probability of B and the intersection. You can use those 3 to find the union. Or maybe you know what the union is, and you know what A is, but you don't know the intersection, right? Or you do know the intersection, and then you could use it to find B, right? So you can take any 3 of these pieces of information to find the fourth, right? And that's kind of the reason behind this addition rule. If you knew all of the information, you wouldn't really need to use it. It's here to fill in gaps, right? So we're going to use this in the future to fill in gaps of things that are missing.